I'm in Electronica talking to Steve Oliver, the Vice President of Sales and Marketing for Vicor's VI chip division. Vicor's always been an innovator in power systems design, and one of the biggest innovations was the introduction of VI chips and the Factorized Power Architecture, FPA. Thanks for talking to me, Steve. Can you bring me up to date with what's happened since the launch of the first VI chip products?
Since the first products were launched, we have been very busy. We've expanded and enhanced the original range of DC to DC products and now have launched the first universal AC input PFM device. This means we have a complete solution from AC to the point of load.
The VI chip products offer some outstanding benefits, particularly in terms of efficiency. Can you explain how this is achieved?
There are two main topology engines or building blocks in VI chip architecture. There's a non-isolated buck-boost engine and the sine amplitude converter. Let me show you a couple of diagrams. Unlike traditional topologies, like a synchronous buck converter, the sine amplitude converter does not have any duty cycle limitations. As a result, we can achieve very high efficiencies from 48 volts direct to 1 volts at up to 90% and 130 amps. The first engine is a non-isolated buck boost, which we call our pre-regulator module or PRM. This takes in an unregulated DC voltage and gives out a regulated and trimmable voltage which feeds into our downstream voltage transformation module or VTM, otherwise known as a sine amplitude converter. This is a fixed ratio isolated DC to DC transformer running on a fixed frequency and high frequency topology. Unlike traditional solutions such as a synchronous buck converter, the sine amplitude converter does not have any of the duty cycle limitations. And so we can achieve very high efficiency conversion from 48 volts direct to 1, for example up to 90% efficiency and 130 amps at 1 volt.
As well as the development of the technology within VI chip modules, the factorized power approach was a completely new way for engineers to design power distribution systems. Can you explain how this differs from traditional methods of power systems design?
In a traditional supply, such as a flyback or a forward converter, there are two functions. There's a regulator function and a transformation function, and usually an isolator also. And these are bonded together in the topology. But that means that if you try to improve the regulation, you may hinder the transformation and vice versa. But if you were to separate or factorize into a separate regulator, our pre-regulator module, the PRM, and a sine amplitude converter, the transformer, our VTM, then they become like building blocks, like Lego, that can be put together in different systems to improve the efficiency, the power density, and the flexibility of the design.
Can you explain how you combine the two elements to achieve the output voltage that you require?
Certainly. Let's look at another slide. As you can see, we have an unregulated voltage going into the PRM regulator. By setting a resistor, we fix the output voltage of the factorized bus at 48 volts, which feeds into the fixed ratio downstream VTM transformer. And the simple mathematics, 48 volts divided by 4, which is the transformer ratio, gives 12 volts. If you'd like a lower or a higher output voltage, by changing the resistor input to the PRM regulator, you adjust the factorized bus voltage, and again, the fixed ratio transformer gives you the output voltage you're looking for.
Okay, and what about systems that require highly regulated supplies?
With VI chips, there are three choices of feedback regulation. There's a simple local loop around the PRM regulator, which gives between 3 and 5% regulation over line and load at the output. A little more advanced is the adaptive loop, which takes a feedback from the VTM transformer to give 1 or 2% regulation. And then finally, a remote sense or remote loop, which feeds back the voltage from the exact point of the load back to the regulator, giving down to 0.2% regulation, which is very tight. This kind of feedback, that's the remote sense or remote loop feedback, which we use for solutions like the Intel VR12 processor.
In applications such as telecommunications and computing, supply voltages are dropping. How do VI chips support this changing requirement?
With newly released PRM regulators with very low trim range and high K-factor VTM transformers of up to K of 1 over 40. This means that today, with mass-produced product, we can deliver 130 amps at 0.125 volts, future-proofing our customers' designs.
That's great. And how do engineers feel about using the FPA approach?
Engineers are very enthusiastic about the high efficiency, high power density, and the factorization of the architecture. For example, the engineers at IBM have used true factorized power architecture in their Power 7 servers.
So, can engineers use VI chips in a conventional intermediate bus design?
Certainly. Whether it is from a high voltage, say 380 volts, or 48 volts down to 12 volts, we have our bus converter module, or BCM, which uses the same sine amplitude converter as the VTM transformer.
Is high efficiency the main reason why someone would use VI chip modules?
Efficiency is very important, but power density, or rather the small size of the components, is also critical. For example, this is our half-chip regulator. That's a half square inch capable of 200 watts of conversion. This is our 1-inch area voltage transformation module. Together, these would convert 48 volts to 1 volt at 130 amps at 90% efficiency. In addition, a traditional power supply would normally have a large bank of capacitors for a good transient response. With the voltage transformation module, this is a very low impedance device, less than 1 milliohm from DC up to a megahertz. This means that when the load wakes up and demands to pull power from that bulk capacitance, it can see through the transformer to the higher voltage rail. As energy stored in a capacitor is related to the square of the voltage, and if this was a K of 1 over 32 transformer, instead of having 1000 microfarads of electrolytic cap here, you can have 1 microfarad of ceramic chip cap on the 48 volt. So you can see it would be a huge energy and size saving.
Okay, and what about lower power applications?
For lower power levels, we now have the half chip range. So this is the half-inch area VI chips. We have the regulators, transformers, and bus converters in this size. So you can see that smaller size, also lower power level, addresses more applications.
And are there any other form factors? Surely some power designers would like an alternative to surface mount products.
Yes. Apart from the traditional VI chip surface mount, we also have a through-hole option. Plus, we have what is known as a VI brick format. This is a ruggedized, thermally adept package featuring pins and a built-in heatsink so that customers can choose the correct package depending on their application.
And Electronica, you're launching VI Chip's first AC-DC product, the PFM. It's the lowest profile AC-DC converter in the world, but can you tell me why it's so important?
The low profile of a 1/4 inch or less than 7 millimeters allows designers to remove the power supply from normal expensive rack space and to hide it down the sides of the rack or even door mounted. So that means they have more routing, switching or computing performance in a given floor area.
And what are the other benefits of using the PFM?
The PFM has an adaptive cell topology, which means that it has very high efficiency over the complete worldwide AC line range and load range. This means that compared to traditional topology, the PFM has less than half the power loss and cooling requirements at low line.
So does the introduction of the PFM mean VI chip products can really deliver a complete power solution?
Certainly. As you can see from this diagram, the PFM creates a safe SELV 48 volts from which downstream VI chips provide power to all of the different loads.
And what about the future? Are there any more developments planned for VI chips?
Vicor invests 15% of gross revenue in research and development. This is 3 to 4 times the industry average. As a result, we have reduced power loss by 25% and improved power density by 25% every 2 years, and we expect this to continue.
It's great to hear you've got so many ideas for developing VI chips and the factorized power architecture. Thanks so much for giving me an update.
You're welcome.